So hello to everybody. This presentation is designed to provide a brief overview of what's called the Levitate project. Within the presentation, I'm going to give a short overview of the project in terms of the aims and objectives, a brief description of the methods, and a very brief overview of the results of the study to date. Levitate stands for Societal Level Impacts of Connected and Automated Vehicles, and the intention is that the project will build tools to help European cities, regions, national governments, etc. prepare for a future with increasing levels of automated vehicles in passenger cars, urban transport services and urban logistics. The project funding is 6.4 million, provided by the European Commission within Horizon 2020, and the project, which is led by University of Loughborough, brings together 12 partners from 10 countries, including renowned research institutions, local authorities and global partners. It's a 3-year project and it started in December 2018. So the overall aim of Levitate can be described as building tools to help European cities and other cities, regions and national governments prepare for a future with what is predicted to be increasing levels of automation in passenger vehicles and other urban transport services and urban logistics. We will eventually develop an impact assessment framework which will be available to policymakers so that they may be able to manage the introduction of automated transport to maximum effect. And this in turn will allow that the technology can be harnessed in order to achieve societal objectives. The main work in Levitate is being conducted in the form of 3 use case work packages. So I'm just going to describe these work packages very briefly. Work package 5, which is use case 1, deals with automated urban transport and is conducting impact assessments and case studies for automated urban transport scenarios. Work package 6 deals with passenger cars and is responsible for conducting impact assessments and case studies for passenger car scenarios. And work package 7 deals with freight transport and logistics and is responsible for conducting impact assessments and case studies for this type of transport. And then finally, of importance is work package 8, which involves the development of what's called a toolkit and implementation of results. And it's also responsible for establishing what we're calling the Levitate policy support tool and populating it with methodologies, case studies and impact assessments. Much of the work that we've conducted to date concerns the consideration of the use cases and looking at the predicted changes that are likely to occur as the use case progresses from theory to concept through to actualization. For example, using both traffic microsimulations and mesoscopic simulations, we've been assessing likely changes to parameters such as journey or travel time, congestion, traffic conflicts, emissions, and the amount of travel people are likely to be involved in. We've developed a system dynamics approach for looking at effects on public health, commuting distance, parking demand, etc. We're using a driving simulator to look at changes in driving behaviour, and we're using operations research to look at metrics such as fleet size, total kilometres driven, and vehicle operating costs. In some cases, we're using a Delphi method, in other words, surveys and questionnaires for scenarios which we cannot approach using the other methods listed. So as you can see here, different approaches have been deemed necessary depending on the specific use case. So for example, with safety, we've been considering likely changes in numbers of injury accidents and changes in crash types and casualty severities. For some impacts, we've been using a mixed methods approach, whereas for others, a singular approach has been used. These are the sub-use cases that I mentioned in the previous slide, and these are the scenarios which really underpin the project in its entirety. These are the metrics that are being examined using the different analysis strategies that we developed within the earlier phases of the project and which I mentioned on the previous slide. For example, within road use pricing, we're looking at things such as road tolls, etc. that might be implemented within city areas. And we're also considering predictions relating to automated ride sharing, parking space regulations, both on-street and off-street parking, provision of dedicated lanes for autonomous vehicles, and consideration of green light optimal speed advisory systems, which advise the vehicle which speed it needs to go at to ensure a green signal at the next set of traffic lights. This is just one example of the approach we're taking within Levitate, and this example applies to the case of parking behaviour. So what we've done is to use a traffic microsimulation modelling platform known as AIMSUN, or Advanced Interactive Microscopic Simulator for Urban and Non-Urban Networks. And then we've modelled a number of possible scenarios using different levels of automation. And the AIMSUN model here is based on the city of Santander in northern Spain. Scenarios in the table show the types of behaviour that are prevalent in terms of the percentage of vehicles, in our case passenger cars, following that type of behaviour. So vehicles may be forced to return to origin, so no parking in the city centre, park outside the city centre area, drive around to avoid parking, park inside the city centre, relating to the people living in the area, etc. And what we've done is modelled different percentages of these behaviours to mimic the different types of scenarios. And as connected and autonomous vehicles penetrate the market further, we will see delays decreasing due to increasing capacity resulting from shorter headway. However, scenarios relating to return to origin shows higher delays due to extra trips generated, which is the graph on the left. This causes congestion, and therefore total amount of travel is also less in comparison to the baseline. Emissions show gradual decrease as autonomous vehicles penetrate the fleet, and this is due to the assumption in our simulation that all autonomous vehicles will be electric vehicles. In another sub-use case, we've been looking at what might happen in cities if we provide dedicated lanes. And this time, you can see the AIMSUN model is based on the city of Manchester in the UK. As you can see here, we've modelled a number of scenarios using a baseline scenario with no dedicated lanes, a motorway with a dedicated lane on the outer part of the motorway, a motorway with a dedicated lane on the inner part of the motorway, a motorway and A road with dedicated lane on the outer part of the motorway and A road, and finally dynamic control with a dedicated lane, but the lane is dynamically controlled. The results show less impacts on delay, amount of travel and emissions for the scenario where a dedicated lane is provided only on the motorway. Providing a dedicated lane on an A road actually worsens the delays and increases congestion. So this just gives you a type or an example of the types of things that we're doing based on the microsimulation modelling. What are we planning to do in the remainder of the project? We will produce impact assessments for each sub-use case identified using relevant methods. We're also going to look at transferability of traffic microsimulation results to different cities. We also intend to produce case studies from driving simulators and individual city-based impact assessments, and also perform benefit and cost analyses. Overall, we expect to achieve a full range of impact assessments for sub-use cases relevant for cities and policymakers alike within what we're calling the policy support tool, which will be available for all to use. And this is the proposed operational model of the policy support tool that will be available at the end of the project. It looks complicated, but it's relatively simplistic. Essentially, the policy support tool will be based on a number of both use cases and sub-use cases, as we saw previously. And users of the policy support tool will be able to assess the impact of a particular parameter, say for example congestion, based on charges that are likely, or changes that are likely to take place as automation becomes more prevalent. And this will allow policymakers to study how congestion in inner city areas might change on different roadways if the composition of the vehicle fleet changes as a result of changes in uptake of autonomous vehicles. So that's the end of the presentation. We're very grateful to the funding that we received under the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 824361. Thank you.